Okay, this is lesson 6 of week 2 of Acids and Bases online learning. So we're going to talk about logs a little bit today. It's not super important that you know how they work, but I'm just going to give you a quick little introduction for kids who maybe aren't in Algebra 2. For all logs, we're going to only use a base of 10. So the way logs work, we have a log with a base of some number x is equal to some number y. And the converse of that would be that whatever the base is to the power of y equals x. Okay, so it's kind of, you can kind of think of it as a way to flip a fraction, so to speak. Okay, so we're only going to use base 10. So if I had something that was log base 10 of 1,000, that would equal 3, because the base of 10 to the third is 1,000. Okay, the log button is just a button in your calculator. So if you were going to do this like in your calculator to see does this actually work, your log button is a base of 10 already. So if you hit log of 1,000, you should get 3 because the log button in your calculator is already at a base of 10. Okay, so it's kind of just a general how logs work sort of thing. Let's say we threw a negative in there. It doesn't really affect anything much, okay? So let's say I had log base 10 of 1 times 10 to the negative 5th. Okay, well, that would equal negative 5. Because if we're taking log base 10 of something times 10, this is like 10 to the third. This is like 10 to the negative 5th. So it is negative 5. So 10 to the negative 5th literally does equal 1 times 10 to the negative 5th. If we stuck a negative in front of the log, if we took negative log base 10 of 1 times 10 to the negative 5th, we would be canceling out the negative in front. So instead of it being negative 5, it'd be negative of negative 5, which would be 5. Crazy, right? So then 10 to the negative 5 is still 1 times 10 to the negative 5. Oh. Sorry about that. My cat jumped in front of the camera. He's an attention hog. Okay, so let's kind of take this and then apply it to our acid-base stuff. Okay, so if you turn to page 3 of your notes, that's where I'm going to kind of start. Okay, so it says acidity is proportional to the concentration of hydronium. We like to use the term hydronium and H plus kind of, we kind of like to change those around. So hydronium really is H3O plus, but a lot of times in literature and on worksheets and stuff, we like to call it H plus, because really it's just water with an extra hydrogen. So either one, it just has an extra proton. It says because the concentrations tend to be very small and vary over a fairly wide range, we use logarithms to describe them, because logarithms make either very, very small numbers into normal numbers or very large numbers into kind of normal, easy numbers. Kw is the equilibrium constant for water, okay? And so you do need to memorize that because we're going to use it in some math, okay? It says this equation describes the water's autoionization. So water reacts with another water molecule to make hydronium and hydroxide. But this only happens to a very, very tiny amount. Only 1 times 10 to the negative 14 of all water molecules in a pure water solution even do this. Most of it stays as pure water, but portions of it, just that much, will dissociate or react in this case. All right, so we have an equation. The Kw, water's ionization constant, is equal to the hydronium times the hydroxide ion concentration. Okay, which is this. Hydronium times hydroxide equals that. Okay, it says the pH of pure water is 7. Okay, so that means you have the same amount of hydronium as you do hydroxide in pure water. Okay, so in pure water, the amount of hydronium is equal to the amount of hydroxide, which is 1 times 10 to the negative 7th molar. If you multiply 1 times 10 to the negative 7th molar times 1 times 10 to the negative 7th molar, you get 1 times 10 to the negative 14th, which is water's ionization constant. Okay, so to kind of flip this around, we want to use log, a logarithmic scale, to give us powers. The P in pH, it basically just stands for a portion of the concentration or a power of the concentration. So nobody really knows what the P stands for, but you can think of it as power because it's going to be to the power of 10 of something because our log base is going to be 10. So this is the equation for how you find pH. pH is the negative log of hydronium ion or hydrogen ion concentration. Okay, so now let's apply those things. Okay, you have like a pH scale at the top of this page, which is kind of fun. So it says, what is the pH of an acid with a concentration of 6.98 times 10 to the negative 5th? So your pH equals negative log of the hydrogen or hydronium ion concentration. Acid is hydrogen ion concentration. So negative log of 6.98 times 10 to the negative 5th. So you literally just stick that in your calculator. Okay, and so that's what you get. Now, sig figs. Your number of sig figs, so I'm going to kind of put this off to the side. Your number of sig figs in the concentration is equal to the number of decimal places in pH and pOH. So this is the sig fig rule for pH and pOH. So since your concentration had 3 sig figs, we have 3 sig figs in our concentration, okay? So we need 3 decimal places in our pH. So then this number rounded to 3 decimal places is 4.156. Okay? And that's the answer. There are no units for pH and pOH. That's the answer. Okay? Okay, so if we want to flip that around using our log scales, right? Let's talk about this for a second. The pH scale for acids, it's less than 7. Your pH has to be less than 7 to be an acid. So if you have something with a really, really low pH, it's probably a strong acid. If you have something that's approaching 7, like it's like around a 5 or a 6, that's probably a weak acid. If you have something that's like a 14, a really, really high pH, that's probably a very strong base. If you have something that's around like an 8 or a 9, that's probably a very weak base. So you do have to understand strengths of acids and bases here as well in terms of numbers, not just amount of dissociation. All right, so it says, is it possible to calculate pH? It's possible to calculate the pH, use the pH, to calculate the concentration of hydrogen ion or hydronium. All right, so then this is the formula for that. So you're going to have to memorize this formula as well. So hydronium is equal to 10 to the negative of the pH. So it says, what's the concentration of acid with a pH of 3.48? So we would do 10 to the negative of 3.48. So you literally put that in your calculator. 10, and you want to use this caret button right below the clear button, caret button. Negative 3.48, and then hit enter. Okay, so then that's your answer. But then we have this sig fig rule. So the number of decimal places in the pH or the pOH is how many sig figs your concentration should have. So this should only have, this has 2 places past the decimal for the pH, so our concentration should only be 2 sig figs. So this would be 3.3 times 10 to the negative 4th. Molar. And that's the answer of, well, acid, hydronium, hydrogen, whatever you want to call it. It doesn't matter, either one. All right, so it says less commonly seen as pOH, okay? So to determine pOH, it's probably easier to start at the bottom of the page, right? pH plus pOH have to equal 14. They have to, okay? Because that's the scale. Now, can there be a negative pH? Can there be a pH greater than 14? Yes, same goes for pOH. Those are super strong things, and yes, that's possible, okay? It is possible. So we have to know that. So we treat it the same way that we treated pH in terms of our formulas. pOH is negative log of the hydroxide ion concentration. So there's our formula for that. We got to memorize it. And OH, hydroxide concentration, is equal to 10 to the negative pOH. So we got to memorize that. So what is the pOH of a base with a concentration of 0.97 molar? So we want to know pOH, so that pOH is equal to negative log of 0.97. So then we stick that in the calculator. And you get 0.0132 blah blah blah. This one is 2 sig figs, so you should go 2 places past the decimal with your pOH. So 0.01. And that's your pOH. Okay? And we want to know the pH for the previous example. Well, if pH plus pOH equals 14, then 14 minus the pOH will give you the pH. So 14 minus 0.01 equals 13.99. That's your pH. You don't even need a calculator for that one. Okay? Alright, so keep going, just a little bit more. Pause anytime, rewind anytime to go back. So for other problems, it may be useful to use this relation. Okay? I try to avoid this one like the plague because it's just a lot of stuff to stick in the calculator at one time, and I don't like pushing that many buttons in the calculator. Alright, so we already highlighted this equation, but now we're going to use it. Okay? So hydronium times hydroxide equals 10 to the negative 14. So it says, what is the hydronium ion if the hydroxide ion concentration is this? Well, we just have to rearrange this formula. So 1 times 10 to the negative 14 divided by the hydroxide ion concentration, which is 4.55 times 10 to the negative 10 will give you the hydronium ion concentration. Okay, so what did I do? I just rearranged this formula. So my hydronium ion concentration now equals 10 to the negative 14, or 1 times 10 to the negative 14 over the hydroxide ion concentration. So all I did was divide both sides by hydroxide to get that formula, and I plugged it in. That's it. So what's tricky is sticking it in your dad-blamed calculator. So I would do, in parentheses, I would do 10 caret negative 14, and then you have to use the arrow to get out of that, parentheses, divided by, open parentheses, 4.55 second, comma, negative 10, close parentheses, equals that. All right, so this is a molarity to molarity, so you're going to use the same number of sig figs. You had 3 sig figs before, you will have 3 sig figs after. So it's 2.197, so 2.20 times 10 to the negative 5th. And that's your hydronium ion concentration. Okay. Now, for this one, it says if you have 95.2 grams of potassium hydroxide and 450 milliliters of water, you want to know the hydroxide, the hydronium, the pH, and the pOH for all of that. So first you have to do a little dimensional analysis. So 95.2 grams of KOH in 450 milliliters. I don't like milliliters. I'm going to do 0.45, and that O goes away because there was no decimal. So 0.45 liters of solution. And then I have to convert that from grams to moles. Okay. Well, potassium is 39.10 plus 16 plus 1.01, 56.11 grams. So then grams of KOH will cancel. You're left with moles over liter, which is molarity. So 95.2 divided by 0.45 divided by 56.11 gives me that. And so that's 3 sig figs, that's 2 sig figs, so my answer must be 2 sig figs. So this is 3.8 molar KOH. Okay, well, since there's only one hydroxide in this, my hydroxide ion concentration is exactly the same. So this means that my hydroxide ion concentration is 3.8 molar. So that's my hydroxide ion concentration. I don't even have to do any math for that. Well, I kind of already did. So if you had 2 hydroxides, you'd have to double this to get your hydroxide ion concentration. But you only have one hydroxide. So it's the same. All right, so let's start with pOH. So pOH is the negative log of the hydroxide ion concentration, which in this case is 3.8. So negative log 3.8. All right, and it's negative because that is a super strong acid and a very high concentration. All right, our base, super strong base, very high concentration. So if my number of sig figs in concentration is 2, then I go 2 places past the decimal. So this is negative 0.58. So that's my pOH. So my pH will be 14 minus my pOH, which in this case is negative 0.58. A negative minus a negative is a positive, so my pH is 14.58, indicating that I have an extremely strong base. Then my hydronium ion concentration is 10 to the negative of the pH, which is negative 14.58. So that would be okay. And so that is going 2 places past the decimal. So my answer should be 2 sig figs. So I get 2.6 times 10 to the negative 15th. That's not a 5. Molar. There we go. And that's the end of lesson 6.